Uh, Hello, this is Team Hyper Updates, and this submission is for Chainlink Constellation Hackathon in Hyper SDK track. So what we are solving is we are securing the over-the-air updates, firmware updates by using integrating blockchain in the overall infrastructure. So first, let's discuss about the problem. The problem is that currently there are only two ways of updating your IoT device, and the first one is like physically connecting to the IoT device using a computer and then pushing the update into it, which is not practical. Organization have to call all their devices into their service center and then update it, or rely on the user to update the firmware device, firmware update. And the second thing is over the air update, which is much more practical and used widely in the industry. Like you have your own car, and it has a lot of IoT devices which is connected to the internet, and this is how your updates are pulled. And the update is pulled from a centralized server. You can see it is called the OEM cloud, but the problem is that it is centralized, and your both hash as well as your firmware binary is uploaded here. So let me give you some stats about these industry. So currently there are 15 billion devices connected to the internet, and it will rise up to 29 or approximately 30 billion as by 2030. And with this much rise in the devices, there will be a lot of security vulnerabilities also. So yeah, in the update infrastructure, there are quite of vulnerabilities there. And first one is your firmware blues attack. You can see which is like compromising your centralized OEM cloud and then uploading the malicious update there, and then the update will be pulled by your whole IoT network, so which is like quite serious attack, and it has rise up to 77%. And you can I've given all the sources here. You can just go to the sources and read it in more detail. All these three vulnerabilities are given in this source. The second one is your DDoS attack, which is distributed denial of service, and your centralized server is attacked by or flooded by multiple requests, and thus enabling your IoT devices to pull updates. And the third one is man in the middle attack, and in which your hacker spoofs in between the network and then upload the malicious update. So in order to like understand how this works, we have to understand how OTA works. So the first thing is you have your firmware update, then you compile it down to a binary and you calculate the hash of that binary, and you upload the hash as well as the binary file into your OEM cloud, and then you pushes a MQTT call to the IoT device that hey, there is a new update, you can pull this update from this URL, and this is how your this device will pull the update. So so the architecture we are fixing is this. So the problem is that your this MQTT call can be spoofed, and like wrong cloud address can be given, and thus your IoT device will pull wrong update, or even spoofing in between, which will result in malicious update bill being installed into the firmware. So this is our architecture. How we can solve is that we replace the OEM cloud with this blockchain network and your vendor service. So this is currently our subnet, and this is our Hyper VM client, and this is your like any blockchain explorer you can use for this, or you can create your own. So here the vendor service pushes your update, which includes your update name, your update hash, your update URL, your binary URL, which is uploaded to your decentralized storage, which is IPFS. And this all is done by your which this hyper update CLI, which we created. So this is pushed to the subnet, and then you create an MQTT call to this hyper OTA, sorry, this IoT device, which with the transaction ID, which calls the blockchain with the transaction ID and pulls the update. But your IoT device cannot call blockchain like there is no library for that, and that's why we developed a custom library for OTA, and we added blockchain support so that your IoT device can call the blockchain or the chain and pull the updates from it. So you can see the whole architecture is secure, because you cannot if you have a lot more like nodes, then your blockchain won't be compromised, and you have immutable ledger in it. So that's why that cannot be like that cannot be like edited by the hacker. So once the update is pushed, there is no way anyone can change that update. So it makes very secure, the overall infrastructure very much secure. So uh, this is our like architecture, and we are planning, we have created this subnet which is your hyper updates VM, and any organization can fork that VM and change it accordingly, and then connect it to the main avalanche, and this is for the future. And when all the subnets are connected with each other, then it will make the whole distribution of firmware updates very much easier. Like anyone can connect to any subnet, and then it can pull the updates from that subnet as well as other subnets also. So the distribution for this, you don't have to, if you want to pull new updates or download new software, you don't have to go to the third party distributors or any website. You can just download a client, and that client will connect to a subnet, and then you can like update any of your software. So this is the overall like problem we are trying to solve, and now I'll demonstrate the working of this. I know that the video is quite long, because the overall thing is quite large to understand. And yeah, so now moving to the demonstration. And in this project structure, we have code for both vendor service as well as our chain. And you can see in this build, this update CLI, which is the CMD update CLI. This is our vendor service, and this one is our chain. And our chain is already running because it takes time to initialize the chain and run it. And your this CMD update CLI, it is a CLI, but it also consists HTTP endpoints which you can query and like do your transactions. And here you can see this chain is built using Hyper SDK, which is developed by Ava Labs. And you can use Hyperledger as well, or uh, uh, other frameworks also, like Polkadot Substrate. But for this use case, for the hackathon, we are building it on Hyper SDK. And here we can run our build update CLI chain watch, just to see the transaction happening inside the chain. So okay, it is running, and we will also start our server. Update CLI. Okay, so now I'll go to my endpoints, HTTP endpoints, and from here I can query our this we can query our vendor service. And also, like we since if you want to do transaction in the blockchain, you should have a wallet, but you cannot implement wallet inside your IoT device. But you can do it by creating a separate service which will handle the wallet thing, and you can expose HTTP or RPC endpoints that your IoT device can call and do the transaction. For Ethereum cases, you can do similar with Infura, which is also the similar kind of service, and we have built this service inside the update CLI only. So uh, if I go here, you can see this Hyper OTA. This library we built using Elegant OTA, which is this Hyper OTA is basically fork of Elegant OTA, and we have changed some code to call our chain and then get the validation of that hash, binary hash. And we will upload this into our ESP32, which is here. Currently it is connected like a wired connection, but this Wi-Fi is connected to my like home router, because like we connected this widely because we wanted to see the serial outputs of whether the update is happening or not. So okay, now I'll upload the initial code to my ESP32. Okay, so it will take a little bit time. Till then, I'll explain you some of the parts, like how my system works. So here we'll call the chain with the binary file, and then binary file will be uploaded to your IPFS to our IPFS server. So IPFS basically is the decentralized storage, and you can even in the presentation I explained you that your binary file will be uploaded to your centralized server, but to add more extra security layer, you can move it to the decentralized storage, so it becomes hard to like gain access to that file. Once you upload that file, you cannot change it, and then your IPFS URL of that file will be uploaded to the chain with the hash of that file. So okay, so our code is uploaded. I'll just monitor it. Okay, so our ESP32 is successfully connected to my Wi-Fi router, and since it is connected now, we can begin our firmware update. So the first thing is creating a project inside the chain. So we'll just call it hyper updates, and we'll upload it. Wait a second. So okay, the response is our transaction ID of this data. So we can just call call the chain using this transaction ID, and we'll get this data back. Now we'll create an update to this transaction ID, so that this transaction ID is basically pointing towards our project, and our single project will have multiple updates for that. So that's why we are pointing it using our transaction ID, our device name, and our version name with the binary file. So what we'll do is we'll just change something here. Uh, we'll change. Uh, okay, we'll change this dot to plus, which means these consecutive dots will be now displayed as plus. We'll compile it again, and then what I'll do is I'll delete this firmware file, and I'll copy it from the build. So okay, the build is successful. We'll copy it, and then we'll paste it here. uh, sorry, we'll paste move it here, and then we'll name it to firmware.bin. We did this because the PIO is like hidden directory, so we can't actually see that from our postman. So now we'll go to documents, platform, my projects. So here you can see our binary file. So now we'll just create an update, and now this will be uploaded to the blockchain. First, the binary file will be uploaded to decentralized storage, which is IPFS, and then the URL of that binary file will be mapped into our chain data. And now to see what is stored inside the chain, we can even see it from here. You can see this transaction being happening in our chain, and also we can see it from here by just calling this endpoint. So you can see uh, this is the IPFS hash of our binary file. So we can just go to this hash and download, but we'll not do that here. So, and also this is the URL for this repository. We have our library for ESP32. We have our chain code here. So okay, so now we'll call this endpoint, which is the most important. Here we will add the transaction ID of the update, and then IP address of our device. Currently it is connected to our local host, which is this one. So we'll just uh, make it like this only, and then we'll just send it. Now if we see here, you can see the update is happening, and this was the URL called by our ESP32 to the vendor service, to sorry the chain, to get the valid transaction, sorry, the valid hash of this firmware update. So we passed that hash that we calculated inside our ESP32, and then we send it to the chain, and the response was valid, and it successfully updated. And remember that I changed this dot to plus, and now you can see it is serial outputting the plus symbol, which means the update is successful. So yep, and to demonstrate some attacks, I cannot do that because this is still in development. But yeah, I cannot attack like the IPFS easily because my binary file is stored in IPFS, so I cannot change that. I cannot change any data inside the blockchain. So it is mostly secured, and uh, you can obviously read this research paper to see their the attacks that they performed and how they secured it. Okay, so thank you.